Welcome to Lyons Township High School, AP Physics. Today we've got a fairly short example involving torque and equilibrium. Let me explain the picture. You might want to copy it down, you might want to pause the video for a second, but once you got it copied, here's what you got. You've got a wall. So it's like maybe a building and there's a wall. And here is a flagpole or some other thing that's holding an object up. You got an object with a weight big W, just to give some numbers to it. Big W, the weight of the sign or stoplight or whatever that is 200 pounds. And the beam itself has a weight of, we'll say, 40 pounds, okay? And then you've got a cable holding this thing up. Without that cable, this whole thing collapses or just it swings down. And there's some dimensions here. The cable's attached 3 meters above this pivot point, or 3 feet, sorry. 1 foot from there, and then the rest of this is 5 feet. So the beam total is 6 feet long, okay? And it's at a right angle to the wall, so there's no angles to worry about there. And what we're going to calculate is very simple. We're going to calculate the tension in that cable and the force that the wall has to apply to the beam to hold it still. And it's going to have 2 components. It's going to have an X and a Y component. So it's a horizontal and a vertical component. Now, I'll mention something real quick. Say it's the greatest setup in the world for a beam. We're going to find the tension in that cable, and you're going to get a pretty big number. So you better have a darn good cable there holding this thing up. So I'll just mention that ahead of time. All right. So the first order of business in a problem like this is to draw an accurate FBD with every force on it and which direction they point. This is actually the hardest part of the problem, and if you do this right, everything else is somewhat easier, okay? So you got a beam, and we're going to draw an FBD of the beam, okay? So I'll draw that down here, and on your paper, I'd suggest you draw it kind of big, give yourself some room. So here's our beam. All right, so what forces act on the beam? Well, you got the weight of this guy. Now, technically, what you have is the tension of this string. It's not the weight of this thing doesn't act on the beam. The weight of this thing acts on this thing, okay? But because this thing ain't moving, we know that this weight is going to equal this tension. And so this tension is going to pull down. And I'll go ahead and label it as big W, even though we know it's not exactly big W, but we know the value of it is the same as big W. So we'll put that there. We have the weight of the beam itself. Now that is on the beam. That's going to be dead center, and that's going to be little w. So you always assume an extended object like this pen, you pretend that all its mass is at the center of mass, and the weight is at the center of mass. Okay, so we got that. We have the string, or the cable holding this thing up, and it kind of goes off like that, right? So I'll call that T for tension, okay? And then we have the wall. Okay, now the wall is going to do 2 things. There's going to be a horizontal and a vertical component to the wall force, okay? You may or may not know which directions those point to start with, okay? So you make guesses. And if you guess wrong, you'll get the right number. It'll just be a negative sign, and you know you guessed wrong. So I will guess up and to the right, okay? And so I'll call this R sub Y, and then this component we'll call R sub X, okay? Now, those of you in the know that this RY is wrong, okay? Can you see why? All right, if I were to take this thing and pivot it here, let's say, all 4 of these forces are going to make this thing go clockwise. So it turns out that RY is going to point down, but we'll just keep it up, and you'll just see that all that happens is you get a negative value. No big deal, okay? And also, those of you in the know might see that Rx is correct. Okay, because if you look in the X direction, there's only 2 forces that act. There's Rx, and there's an X component of tension, and they have to be the same. And so this is actually pointing the right way. This guy not, but again, pretend you didn't know that. We'll see what happens. Okay, so we know that anything in static equilibrium has several conditions, the 2 major conditions. We know the net force on that object is 0. Not only that, we know the net force in any direction we choose to look at is 0. We also know the net torque is 0. And same thing, the net torque about any point you want to pick is 0. This thing ain't moving. So the torque, no matter what point I pick, whether it's here or here or here or here, the net torque about any of those points is going to be 0. Okay? So we'll start with net force. And you can pick any direction you want to look at. I'll look at the x direction first. Now there is an angle up here. Okay? We need to know that angle. And so that's a little trig. Now you got a little right triangle here, yeah? So like the inverse tangent of that angle would be 3/1. Or tangent of the angle is 3/1. So the inverse tangent will be the angle. I took the liberty of calculating that. I got about 71.6 degrees. Okay? So that's that angle there. So in the x direction, so the net force in the x direction has to be 0. All right? So I've got, I'll say right's positive. So I've got Rx to the right. And then there's a component of tension pointing left, and that would be the adjacent leg of the triangle that tension would form. That would be the t times cosine of the angle. That's the adjacent leg. So minus t cosine of that angle, which I know, this has to equal 0. So I've got an equation, and I know theta, so I know cosine of theta, but there's two unknowns. I don't know Rx, I don't know t. So I've got two unknowns, I only got one equation. So I got to come up with a second equation. So I'll do the y direction. Net force in the y direction has got to be 0, right? All right, we'll say up is positive, okay? So in this case, I got Ry pointing up. I've got the component of tension that points upwards, so this is our diagonal or hypotenuse. The vertical component of tension would be t sine of that angle. So this would be t sine of that angle. Now again, I know that angle, so I'm good with that. And then these both point down. So minus little w minus big W equals 0. Little w is 40, big W is 240, so that's minus 240. I'll put it over here and make it a positive 240. So you get Ry plus t sine of the angle equals 240. Okay? So I got my second equation, but I've introduced a third unknown. I don't know what Ry is. So I got to come up with a third equation. So the third equation will be net torque. Now for that, I'm going to say net torque about any spot I want has to be 0. Okay, so the question is, which spot do you pick? Well, you can pick any of them, and any of them will work, okay? But there are often more convenient spots than others. I tend to pick a spot that has many forces going through it. In this diagram, this spot has the most forces going through it. It's got 2. Now, I picked that spot because when a force goes through an axis, that force causes 0 torque. So if I pick this spot to analyze, this force and this force cause 0 torque. So they're out of the picture. So then I've only got these 3 guys left. Okay? Now, by the way, I only got these 3 guys left, and only one of them is unknown. So I'm going to immediately be able to find that tension in that cable. Okay? So that torque is 0. So I'm going to say 0 equals. Now, I will say that clockwise is positive. Okay? So if here's your bridge, the tension is trying to pull it counterclockwise, so that'll be a negative. Okay? Now when you find torque, and I'll write this down off this side here, torque is R cross F. Okay? So again, cross product means how perpendicular, okay, is the R to the F. So what you want here is you want the component of tension that's perpendicular to your beam, okay? So this is 1 foot, that's your radius, okay? And then you want t sine theta. That's the component of tension that's perpendicular to that radius, okay? So we've got the radius, which from here to here is 1 foot, okay, times F, which is t sine of theta. And again, I know theta is 71.6 degrees, okay? Both W's cause positive torque. They're both trying to make this thing spin clockwise. Now, they are applied at different radii. Now, thankfully, they're both perpendicular to the beam, so that makes it simple. But they're both positive. So we got positive little w times to the center of the beam from here is 3 feet. And we got plus big W times that distance is 6 feet. Okay. Cool part is I know all those numbers except for T, but I know everything else, so I can immediately solve for tension. Okay, so I'll do that in the next board here. All right, so I get, if I plug in for little w, that's 40, and big W, that's 200. So if I plug those in, move this over here, make it positive, divide by sine of theta, I get T equals 40 times 3 plus 200 times 6 all over sine of 71.6. And boom, I got my tension, all right? I took the liberty of calculating that, and I got about 1391. So my tension in that cable is 1,391 pounds. Now, that's a lot. That's like a small car, okay? So it better be a good cable. All right, so that's your tension. Now, once you've got that, finding everything else is very simple. If you plug that back into, let's say here, Rx is simply 13, I'll write it down here. Let's see, it's green. So Rx is equal, I'll move it over here, it's T cosine of the angle. The tension was 1391. So 1391 cosine of 71.6, and you're going to get Rx. And when I did that, what did I get? I got 439 pounds. So that's 439 pounds. And then Ry would be 240 minus that, okay? So Ry is going to be 240 minus the tension, which is 1391 sine of your angle, which is 71.6 degrees. And if you do that, I got negative 1,080 within rounding. So what's the negative mean? Like we said at the beginning of the problem, it means you guessed wrong. Ry should actually point down. Okay, so if you had this thing and you were holding it here, okay, and you have some weights hanging from here, you have to push, the wall has to push down on this, over here, down on this to hold this thing up with, in this case, over 1,000 pounds. So that's a big force. So that's an equation with torque and equilibrium. I hope that was helpful, and thank you very much.